Hello everyone, welcome to another robotics session. Today we're going to talk about robot dynamics. So far we were considering joints and end effector positions and velocities, and we didn't really talk about acceleration or what happens when there is a force applied to the robot. Today we're going to take a look at dynamics of the robots. Why do we need to consider robot dynamics? Because sometimes robots are used to apply forces or interact with the environment around them, which includes applying force or forces being applied to the robots. Therefore, dynamic study of the robots is as important as their kinematics. Before we start diving into dynamics, we need to look at the static of the robots. What's the difference between the statics and dynamics? Dynamics includes the motion of an object, studying the motion of an object through time and considering the different elements of the motion, including mass of an object, forces applied to the object, acceleration of object. A static is when we look at an object that is moving, but at a specific time instant, and we consider that the object is at an equilibrium position, and then we look at it when the time is frozen. We look at the effects of forces or torques applied to the object. So static is sort of a gateway towards dynamic. Consider a robot like this when it's static. So it's not moving right now, right? But there is a combination of forces and torques applied to it. For instance, there's a force at its end effector, and in order to maintain this force and stay static, the joints are applying torque at the joints here. Consider there are motors that are applying torques to hold that force at the tip of the end effector. One question is, how can we relate these forces to torques? It's important for two reasons. One is that we need to understand the relationship between these two in order to go toward dynamic modeling. Second is, it's very important in design of the robots. For instance, you want a robot to have a capability that apply a force of 20 Newton or carry an object with the weight of 2 kilograms. What should be the torque of the motors that you use in the joints? Or even what type of robots should you use to apply this force or carry this load? This is a study of the torque and forces. In order to pick the proper motors that can carry a specific load for us in the robot, we need to understand this relationship. And before we begin, we have a brief review of some of the concepts from basic physics of rigid bodies. Static equilibrium is when an object is in a steady state and it's not moving really, but the combination of forces and torques around it and make sure it stays in an equilibrium position. So statics is essentially studying the equilibrium of objects. What does equilibrium means? Equilibrium means that in uh, Newtonian terms means where the work done by forces or torques on the object applied to the object is zero. Basically, the magnitude of forces and torques that are applied to the object do no work. They cannot move the object. If an object is not moving and essentially it's not an equilibrium, then there is a force magnitude of the forces applied to it are bigger than zero. From Newton laws, you know that when there is a force applied to an object, it moves by a certain acceleration related using these law. So when the summation of forces applied to the object are zero, then the object is not moving and acceleration is zero. This is where we say the object is an equilibrium. Now, we need to also consider the concept of work. What is work? Remember from basic physics, work is the force applied to the object multiplied by how much it moves. For instance, if I have an object that is under a force of 2 Newton, and I use this force to move it by 1 meter, then the work is 2 times 1 Newton meter. Work can be positive or negative. If I move this object in a reverse direction, then it would be negative. And potentially, work is a term of energy and can be related to kinetic energy of the object. For instance, if I apply this force to this object, the work done is 2. It's also equal to the change in the kinetic energy of the object. So if it was essentially at the beginning stationary but suddenly moves, assume the mass of the object is 1 kilogram, then the velocity would be 2. So work, when you apply work to an object, it transfers into kinetic energy and moves the object. There's a concept of principle of virtual work. You might have heard it in your physics courses. But principle of virtual work is when we apply work, the concept of work to an object that is at equilibrium. Remember when we said there is equilibrium, uh, the object is not moving. Summation of forces or torques applied are 0. What does it mean? It means that when it's not moving and the summation of forces are 0, then the work is also 0. Summation of all the works that the forces are doing are 0. What does it mean in mathematical terms? It means that the force applied to an object plus the torques applied to it, they do not move the object. So the overall work is 0. Principle of virtual work says if we assume an object is at the equilibrium and we slightly move it, so assume we increase delta x so it's not 0 anymore, and delta theta so it's not with 0 anymore. Then at the static equilibrium, still the summation of work should be 0. So it means that the force and torque should cancel out each other, or this equation. This is the principle of virtual work. So when an object is at the equilibrium and you slightly move or rotate it, it should turn back to its original position. Summation of forces and torques acting on it should bring it back to equilibrium. So the work done by virtual displacements overall are 0 and should cancel out each other. Why is it important and why did I bring it up? Principle of virtual work is a nice method that we can use to study statistics of robots, statics of the robot, using the concepts that we have already learned, such as forward kinematics. Consider a robot that, let's say, has 2 links here, three links with joints here, and there is a force applied to it. Let's say the motors at the joints apply a torque to stay at the equilibrium, so the robot is not moving. What is the velocity kinematics equation? We've used this equation a lot so far. And now let's use the principle of virtual work. So if it's at equilibrium, if the joints of the robot or end effector of the robot moves slightly, it should come back to its position. So summation of the work done by forces and torques are 0. In other terms, the force times the change in the end effector position are equal to torques times the change in the joint positions. So if we move the joints slightly, the force should move the end effector by delta x and bring it back to its position. This is the principle of virtual work. Now consider the work equation and I divide it by time. What would I get? And it's good to keep track the dimension of these vectors and matrices as well. So assume our end effector position is x and y. The force that we have has two components, Fx and Fy. And our joint space are theta 1, theta 2, theta 3. We have three joints. So delta theta is 3 by 1. This term transpose of torque is 1 by 3, 2 by 1, 1 by 2, and 2 by 1. So these two are scalar values. When we divided this by delta t, what is this term? This is actually x dot, this is q dot. Now let's replace x dot from the forward kinematics equation. What would I get? Cancelling this out and taking the transpose again. This is a very nice equation that relates the forces at the robot end effector to the torques applied at the joints using the Jacobian. So this is another nice feature of Jacobian that we calculated. Jacobian transpose can map the forces at the robot end effector into torques at the robot's joints. This is a nice equation that we often use in design of the robots. As I said, for instance, you want to know if your robot can handle an object that weighs 2 kilograms. You already have calculated robot Jacobian using the methods that we discussed. You can estimate what would be the torque required at the joints. You can see if the motors that you have at the joints are enough to apply the torque. We have used this equation before. You remember when we talked about singularities, I said once that we can use Jacobian transpose to avoid singularities. The inverse kinematic equation that we calculated was given by some equation like this when we use pseudo-inverse of Jacobian. We said you can replace pseudo-inverse by Jacobian transpose and it will help. Why? Because essentially, as we drive, Jacobian transpose maps forces to the torques at the joints. And when we use this equation, use Jacobian transpose, it's like that we're mapping a force equal or proportional to the change in the position of the robot end effector into the joints. What is this force change in the position of the robot? It's like a spring attached to the robot end effector. And as it moves, this spring will pull on it. So when we're solving the inverse kinematics, we assume there's an imaginary spring that pushes us toward where the end effector should be. And how does it help with the singularities? Consider a robot that becomes singular. When the robot is singular, all the positions are aligned. And then it cannot move in one specific direction. Let's say this. But if there are forces, like spring-like forces applied to it, it would assist it to move into that direction. It's like suddenly you try to tip it in one other direction. Get it out of singularity. That's why this method helps and improves the robot performance when there is singularity. So if we replace Jacobian, pseudo-Jacobian with transpose, it's like an imaginary spring is always pushing the robot tip in a direction outside of the singularity toward the robot desired position. This was an introduction to statics of the robots and how we can relate force and torques for the robot at an equilibrium. In the next video, we talk about when we're not at equilibrium and the robot is in motion.